5.6 Electromagnetism. So for this topic, we'll be looking at magnetic effect of a current, applications of the magnetic effect of a current, force on a current carrying conductor, and the DC motor. So for magnetic effect of a current, we'll first take a look at current flowing through a straight wire. So over here, assuming you have a straight wire with a current flowing through it, like this, it'll create a magnetic field in a circular motion. So how do you determine the direction of the magnetic field? You'll be using the right hand grip rule, as shown in this figure over here. So how this works is that your thumb will point in the same direction as the current flowing through the wire. Your fingers, the tip of your fingers would show the direction of your magnetic field. So for this diagram, your current is flowing downwards, so your thumb would point downwards and your fingers will curl in this direction. So, as shown in this diagram, this is correct. Your magnetic field lines goes in the clockwise direction. Now for this diagram, you see a dot. So, in your syllabus, you learn that crosses represent into the paper and dots mean out of the paper. So for here, it means that the dot shows that your current is flowing out of the paper. So what you do is, using right hand grip rule, you put your thumb there and it points towards yourself. Then you look at your fingers and you follow the lines from your knuckles to your fingertip. And you realize that if you use this, your arrows are actually supposed to go this way. So these arrows are in the wrong direction and the magnetic field lines should go in the anti-clockwise direction. Next, we'll be taking a look at solenoids. So over here you can see that it's quite sophisticated how a solenoid works. So I'll start with this diagram over here. So you see the field lines. Whatever comes out from the end shows the north pole. Whatever goes in shows the south pole. So what happens is that the solenoid it consists of a wire curled up into a spiral shape. So here they're showing you that around the wire there's actually small magnetic fields created, and when you combine them together you end up with these magnetic field lines over here. Okay, so for this diagram it shows you that there's a battery connected to the solenoid. So assuming you are not given your poles over here and the magnetic field lines, how do you determine which side is the north and the south? So what you do is you use right hand grip rule. Again, your thumb will represent the north pole. So what you do is that using your fingers, you realize that your current goes through here, it goes in, it goes down at the end, down at the end, down at the end, all the way here. So what you do with your fingers on your right hand, you curl them such that your fingertips point downwards in that area over there. And you realize when you stick out your thumb exits at this side. So this would be your north pole. And then when you draw the field lines, you don't draw this diagram. Which basically means you don't need to draw all these small circles over here. You just combine everything to get this field line. Now for this diagram, it shows you the crosses and dots again. So what happens is that you follow the crosses and dots, your fingers, the fingertips enters into these crosses over here to show that the current is going into the paper. So your knuckles are actually here, and then your fingertips are actually at this end. So when you curl it up using right hand grip rule, your north pole again will be over here and your south pole will be again over here. So what affects the magnetic field strength and the direction of the magnetic field? So an increase in current increases the magnetic field strength. And to represent an increase or decrease in magnetic field strength, we use the field lines. So more magnetic field strength means more magnetic field lines. The weaker the magnetic field strength, the fewer the field lines. As for the change of direction of current, such as we had in this diagram just now. When you change the direction, your initial north-south would change to south-north. So your arrows would change direction for the magnetic field lines, because current changes the direction of the magnetic field. Part B. The applications of magnetic effect of a current. So what a magnetic effect of a current can do is that it can be used in a circuit breaker. So when you have excess current flowing through, such as the live wire through this, it induces a magnet with the south pole here and the north pole here using the right hand grip rule, which would then attract your contact over here. So your contact, which was initially like this, would then be tilted over here, and there will not be a closed circuit. So there will be open circuit over here. So this would prevent the excess flow of current through the wire. The spring here will ensure that once the current stops flowing through, the spring here ensures that once the current stops flowing through, your contact would then be in contact with the circuit again, closing the circuit, and your current will continue flowing through the circuit again. Over here is another circuit breaker. Over here is another circuit which is the opposite of a circuit breaker. So what happens is that when you close the switch, you create an electromagnet which will attract this over here, which would push up this switch, second switch, and make a closed circuit such that whatever appliance you're using can be used. So over here is a double circuit, the first being the electromagnet, the second being the switch that you're closing. Part C. Force on a current carrying conductor. So the experiment to prove that there's a force acting on the current carrying conductor is shown over here. So what you do is that you have a circuit over here with two magnets, one with the north pole facing at this side to the wire, the other with the south pole facing to the wire over here. And you have mercury here because mercury is a conductor of electricity, so that you can observe what happens. And because mercury is used, and because mercury is in liquid state, it can allow the wire to move freely. So what happens is that when you close the circuit, current would flow through here, here, and here, and you set up a magnetic field. So using your right hand grip rule, using your Fleming's left hand rule, you have an induced force. So Fleming's left hand rule consists of your second index finger, middle finger, and your thumb. So using Fleming's left hand rule, if you were to follow your magnetic field lines, which points this way, current going downward, you will have a force that will be going out of the paper. This is your F. It will be pushing the wire out of the paper, and your wire would move in this direction. Over here is a magnetic field into the page as shown by the crosses, and you're putting an electron beam into the magnetic field. So what happens is that this electron beam is negatively charged, and it is opposite in direction to that of the conventional current. So using Fleming's left hand rule, pointing your index finger into the page, your middle finger to the left of conventional current, you will end up with a force that points downwards. So on this slide, I've shown you what Fleming's left hand rule is. So basically, you use your left hand, you put your thumb up, your index finger in, and your current here. And all these are perpendicular to each other. So if you're wondering how to remember which finger holds what properties and does what, you remember FBI over here, starting with your index finger. So when you count 1, 2, 3, remember it as FBI. B is used because for the symbols of magnetic field, B represents magnetic field, and I represents current, and F is force. And here is an equation that will often be used, although it is not in your syllabus, but it's good to know, especially in the explanation of motors later on. So on a straight current carrying conductor, using Fleming's left-hand rule, your magnetic field index fingers follows the arrow of the field lines. So your index finger will point to this direction, your current goes into the page, so your middle finger points into the page, and you realize that the force, which is your thumb, points downward naturally. So Fleming's left-hand rule is often used to find the induced force. Remember this, it's only used to find the force, or the magnetic field, the direction of the magnetic field and the current which creates the force. So Fleming's left-hand rule is only if you create the force or induce a force. Now on this slide, I'm showing you two current carrying conducting wires, and this is the resultant of what happens when firstly the current is flowing in the same direction, and secondly when they are flowing in different directions. So for A, you see the dot, which means that current is flowing out of the paper. For B, it's a cross, which means current is flowing into the paper. So when you have current carrying conductors that are flowing in opposite directions, you get a repulsion. Why is this so? It's very easy to explain. Using your right hand grip rule, you just draw your field lines, and you realize that they point in the same direction in the center. In the center, they point at the same direction. So the field lines cannot be combined, and there's a repulsion over here. But if they're in the same direction, you realize that the outer, because over here the field lines point in opposite direction towards the end, but over here if they're in the same direction for the currents, you can actually combine the field lines to create a greater magnetic field, and there will be a neutral point over here somewhere in the center. The same goes for current flowing into the page for both wires. Part D, the last segment of electromagnetism. So I'm going to teach you about the DC motor. So the DC motor works on the basis of creating a force due to the interactions of two magnetic fields, one from the wire, the current flowing through the wire, and the second through magnets, such as over here. So what happens is that you have a DC circuit over here, and current is flowing through the circuit over here into this area here, creating a magnetic field and the wires over here. So this is a coil, and it is in between two magnets which have set up a magnetic field. So I'm going to draw over here the north and south magnets. So between the two magnets, there's a magnetic field already set up in this direction. Now when the current flows through here, using Fleming's left-hand rule, you can derive the direction of the force. So assuming the coil is in this position, your current is into the paper, middle fingers pointing into the paper, index fingers pointing to the right, your thumb would point downwards, and your force would act downwards. Now what about the left side? So since the DC motor is a rotating coil, both sides must rotate in the same direction, as in it must create a same moment, the moment in the same direction. So over here, when you reverse the position of your middle finger, to show the change in direction of current, your force would point upwards. So your total moment created by both forces would be in a clockwise direction. So this would cause a rotating coil. However, for DC motors, you realize that once your coil looks somewhat like this, once your coil is perpendicular, so it looks like this, your current flowing through it will be here and here if there was no split ring commutator. And you realize that if you were to use Fleming's left-hand rule, your forces would remain upwards and downwards, and the coil cannot rotate anymore. So the whole purpose of using a split ring commutator is to ensure that the coil can rotate continuously. So what happens is that at these positions, when your coil is perpendicular to the horizontal axis, there will be this gap over here with the carbon brushes, so it will be an open circuit. So what happens is that from the previous, before it was an open circuit, previously there was a coil that was moving. Maybe this is a 2D diagram of it. So the force is applying this way. So at this position there's no force acting on it, but because of the moment previously, it will continue to rotate until this position, where the current would change sides because it's a split ring. So the currents change side, and you will experience a force in this direction, and it will continue rotating. So why the coil continues rotating when there's no current flowing through it is because of the inertia of the coil. It was already rotating previously, and because of the previous moment, it will continue to rotate until it gets to this position when the split ring commutator again touches the carbon brushes and it's not at the open gap, causing the current to change direction and the motor to continue moving due to the change in direction due to the induced force created by the current, by the interaction of both magnetic fields. So what happens if you increase the current? When you increase the current, your magnetic field increases in strength. So this increases the force exerted on the wire, and it increases the turning effect. Remember that turning effect, moments, is equals to force times the perpendicular distance. So when this increases, your turning effect increases. By increasing the number of turns of the coil, you will cause a greater magnetic field strength, increasing F as well, because the field strength, or greater magnetic field strength, is equals to F equals BIL. Increasing B will mean an increase in F, and increase in F will mean a greater turning effect. For a stronger magnet, again it increases magnetic field. So increase B which increases F, which then increases moments. So basically, remember that current, number of turns, and the strength of the magnet is increasing the magnetic field strength, which increases the force, and then increases the moment or the turning effect created by the coil.